Have you ever really stopped to think about what happens when you double-click an icon on your computer? I mean, it feels completely instant, right? But underneath that simple click, there's this incredible, super fast conversation happening between your program and the real boss of your computer, the operating system. So let's pull back the curtain and follow that hidden journey. Okay, so let's really get into this. A program, any program, whether it's your browser or game, is really just a long list of instructions for your computer's brain, the CPU. So what's to stop a buggy program, or even a malicious one, from just going wild and, I don't know, reading your private files or wiping your hard drive? Well, the answer is this powerful, invisible manager that's always on duty, your operating system. Just think about the most basic stuff a program does. When you type something, the program has to read those keystrokes from your keyboard. When it shows you something, it needs to put pixels on the screen. Both of those things mean talking directly to hardware. And here's the thing. For the safety and stability of your entire system, normal programs just aren't allowed to do that. They kind of live in a protected, restricted sandbox. So this brings us to a really fundamental idea, a division of power. On one side, you've got your user program, which has very limited privileges. And on the other, you have the OS kernel. That's the absolute core of the operating system, and it has full, total privileges. This slide lays it out perfectly. The user program is like a citizen. You can't just go out and build your own highway or print your own money. You have to ask the government, the OS kernel, which has all the power and control to actually get things done. And that formal request has a name. It's called a system call. It is the official, secure bridge between the program's limited little world and the kernel's all-powerful one. Anytime a program needs to touch hardware or use some protected resource, it has to use a system call. An OS like Linux actually keeps a whole table of these valid requests, almost like a menu, where each service has a unique number. So this flow here shows exactly how it works. Let's walk through it. Okay, step 1. Your program needs to read a file from the disk. Simple enough. So in step 2, it issues that formal system call instruction. Now step 3, this is the crucial moment. Control is immediately handed over from your program to the OS kernel. The kernel is in charge now. In step 4, it does the heavy lifting. It talks to the disk drive, gets the data. And once the job's done, we get to step 5. The OS hands control and the data right back to your program. But there's a potential problem here. A huge bottleneck. Your CPU is ridiculously fast, but hardware like a disk drive, what we call an I/O or input-output device, is by comparison incredibly slow. In the old days, after the OS made a request, the CPU would just have to sit there, waiting, constantly checking in with the hardware, asking, "Are you done yet? How about now? Are you done?" This method, called programmed I/O, was just a massive waste of the CPU's time. So, of course, modern operating systems have a much smarter way of doing things. The OS gives the hardware its commands, and then it immediately tells the CPU, "All right, this is going to take a while. Go do something else useful." The CPU is then totally free to run other programs or handle other things in the background. This is really the secret sauce that makes multitasking possible. But that leaves a big question, right? How does the CPU know when that original job is finally finished? Well, it knows because of a brilliant little thing called an interrupt. An interrupt is literally a signal that the hardware device sends back to the CPU. It's basically the hardware tapping the CPU on the shoulder and saying, "Hey, remember that file you asked me to read? Well, I'm done. The data's ready for you." That signal immediately interrupts whatever the CPU is doing and pulls its attention back to the OS so it can handle the finished task. And you have to remember, during that so-called waiting period, the operating system is not just sitting around. Oh no. It's performing this massive, incredible juggling act you see here. It's managing every other program that's running. It's protecting memory so programs don't step on each other. It's organizing the file system, and it's handling every other I/O request. It is the master coordinator, making sure everything is running as efficiently as possible. So once that interrupt signal finally arrives, the OS jumps back into action. It grabs the data that the hardware got ready, that character from your keyboard or that chunk of a file from the disk, and then it seamlessly gives control right back to the program that asked for it in the first place. The program gets its data and just keeps on going as if no time has passed at all. The whole loop is complete. So the next time you're using your computer, just remember this. You're not really running a bunch of separate, isolated programs. What you're actually watching is an entire, complex society of them, all competing for resources, all being managed and protected and coordinated by one single entity, the silent, powerful, and absolutely essential operating system.